want you to take a look at this video and make sure you correct your answers to the homework. We're going to be looking at the answers to the Chapter 5 Quantum Numbers Electron Configurations Review Worksheet, as well as the Exceptions, Other Info, Ground, Excited, and Impossible State Worksheet. So let's start with 1 through 15 on the Chapter 5 Quantum Numbers Electron Configurations Review Worksheet. Please edit your papers. If you missed any of these, take a little bit of time to go back, look at your periodic table, and if you have any outstanding questions, then next time that we meet with our live class, I will address any questions you have. Just make sure you either highlight or circle the ones you want us to go over, so that will help you find the ones that we need to go over faster. And when I'm checking over your homework, it will let me see which ones that y'all had questions on too. So I'll kind of have a heads up of which ones we need to address in class. So again, edit your papers, and this will go in your exit ticket for today. For number 1, you should have said 5. It says, how many subshells or orientations does a d orbital have? That is 5. D has 5 orientations. Number 2 was 2 directions. The electron can spin clockwise and counterclockwise. Number 3, one of the 4 quantum numbers for the last electrons in fermium. So N is 5, L is 3, M is 0, and S is a negative 1/2. For number 4, I gave you the quantum numbers, 5, 3, 0, negative 1/2, which is what you had up here too. So this was fermium again. So if you identify the element, it's fermium. Both of these were for fermium. Number 5 was 1. It takes only the S quantum number to indicate the spin direction. Number 5 said, how many quantum numbers are needed to indicate the spin direction of an electron? So if all you want to indicate is the direction it is spinning, you only need the spin quantum number. So it takes 1 quantum number for the spin. Number 6 said, how many quantum numbers are needed to indicate the shape of your orbital? Well, it only takes 1 quantum number for that too. 1 quantum number, the L quantum number, tells you the shape of your orbital. Number 7, write the longhand electron configuration for zirconium, Zr. Longhand, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d2. Number 8, another longhand electron configuration, this time for bismuth. So let me zoom out just a little so you can see it all. I'm sorry, for samarium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 5d1, 4f5. Number 9, I want you to do shorthand for bismuth. So for that one, you're going to put xenon in square brackets. 6s2, 4f14, 5d10, 6p3. Number 10, wanted you to identify the 5th energy level element with a full valence shell. What you have to understand about elements that have full valence shell is the only elements that have a full valence shell are the noble gases. So what you want to do is find the noble gas that is in the 5th energy level. So of course that is xenon. If you look at your periodic table, 5th energy level noble gas is xenon. Number 11 said, write the shorthand electron configuration for copper. Remember, copper and chromium are your 2 exceptions to the electron configuration, so you got to remember that. Copper's shorthand would be argon in square brackets, 4s1, 3d10. Number 12 wanted you to determine the maximum number of electrons that can fit in the 6th energy level. So we're going to use the 2n squared rule here for that. We know the energy level is 6. So if you plug in 6 for n and you use order of operations, you're going to square the 6, which is 36, and then multiply by 2, and that gives you 72 total electrons could completely fill the sixth energy level. For 13, I wanted you to identify the element based on the electron configuration I gave you. Then I wanted you to determine the highest occupied energy level, tell me the valence electrons, and the number of core electrons. So if you add up all of your superscripts, they added up to 31 electrons. So element number 31, of course, is gallium, Ga. The next thing was determine the highest occupied energy level. It's the fourth energy level. Let's look at our electron configuration that I gave you. So when you're looking at your electron configurations class, the energy levels are represented by the N quantum number. So this is the first energy level. This is the second energy level, second energy level, third, fourth, third, and fourth. So the fourth energy level is the highest energy level that is occupied by electrons. There's 2 in the s orbital and 1 in the p orbital. So the fourth energy level is the highest occupied. And so that is, once you identify that, that is how you determine how many valence electrons that atom has. So if you add up all the electrons in the fourth, there's 2 in the s orbital and 1 in the p orbital. 2 plus 1 is 3 valence electrons. So you should have said that there were 3 valence electrons, and then that leaves the remaining electrons, or what we call the core electrons. So, so your 31 was your total, minus 3 gave you 28 core. Number 14, that was an impossible electron configuration because you cannot have a d orbital with 14 electrons in it. Notice in the electron configuration, I said 3d14. That's impossible. Never going to happen, ever. Can't happen. The d can only hold 10 max. 15 was the ground state electron configuration. That gave you 32 electrons, and that is exactly how you would write the electron configuration for germanium. So you should have said ground state for germanium. So those are the answers to the Chapter 5 Quantum Numbers Electron Configurations worksheet. The other part of your homework was titled Exceptions, Other Information, Ground Excited, and Impossible. So let's look at these answers next. Number 1, what can be said concerning half-filled and full atomic orbitals? Half-filled and full atomic orbitals. Well, we can say they're extremely stable. For number 2, it says, which of the following is considered stable? So again, it's piggybacking on this topic of what is more stable, half-filled and full atomic orbitals. There were 4 of these that were either half-filled or filled. 2 electrons in the s orbital will be an s2. That's full for an s, so that is very stable. 1 in the s is s1. That's half full. That is extremely stable too. 2 in the p is neither full nor half full, so that's not extremely stable. 7 in the f gives you an f7. Well, that's half full because the f can hold either 7 for half full or 14 for full, so that's stable. And e was the other. D5 is a half full d orbital. So there were 4 of these that were extremely stable that fit the full or half fill criteria. So A, B, D, and E. Number 3 says write the correct electron configuration. And remember, these are your 2 exceptions. So I put argon in brackets, 4s1, 3d5. That is the shorthand for chromium. And then copper is argon in brackets, 4s1, 3d10. You could have done longhand for this. It did not specify. So if they don't specify, you can do shorthand. Number 4, the phenomena of electrons jumping from one orbital to another to obtain either a full or half-filled orbital is called what? Well, in the notes, we said it's called electron promotion. That's what happens when one of the s electrons jumps over and half-fills the d here, and then one of the s electrons here jumps over and fills the d here. That's called electron promotion. One of the electrons gets promoted to the next energy level to make either a full or half-filled orbital. Number 5, the element was germanium because there were 32 electrons. The highest occupied energy level is the 4th. There are 4 valence electrons. Notice I circled the highest occupied energy level, and you add those superscripts. 2 plus 2 is 4. The remaining electrons are considered core electrons. So remember, the core and the valence have to add up to the total. So to get your core, the easiest way is just take your total, 32, and subtract your valence from it, and that gives you 28. Number 6, there were 74 electrons here, which means that's tungsten, W. Highest occupied energy level was the 6th. There are 2 valence electrons, 72 core electrons. Here are your 2 valence electrons right here. Number 7, A, B, and C. These definitions come straight from the notes, but the ground state is the electron configuration exactly like you would normally write it when the atom is most stable. The excited state usually happens when you add electricity or heat, and the electrons temporarily, excuse me, go to an excited state. And so that's a temporary state, and they'll eventually fall back down. And then impossible is just simply never going to happen. If you take a look at A through E, I've given you some electron configurations, and I want you to tell me if they're impossible, excited, or ground state. Eight A is impossible because you can never have a 3s3. 8B was excited. If you add your electrons up, they add up to, for krypton, I got a total of 36. And the problem is krypton normally would end in a 4p6, but so what happened is the electron prematurely got jolted up to the next higher energy level. It will eventually fall back down. This is temporary, but it's excited. C is ground state for chromium because that is how you would write chromium. That is his stable electron configuration. D was impossible because you cannot have 7 electrons in a p orbital. The p is full once it gets 6 in it. And E is ground state for copper because he is your exception also. And so copper and chromium are the 2 exceptions. You do not want to forget those. All right, those are the answers to last night's homework. Make sure you correct your papers and that you include these corrected answers in your exit ticket.